All right, hello everyone. Thank you for joining us today. Chris, why don't you take it away?
Sure. Welcome everyone to another live session for the online astronomy class. Pleased to be here, just back from Hawaii, where the professional astronomers had their semi-annual meeting in Honolulu. Obviously not a hardship assignment in January to go to Honolulu, although Tucson's pretty nice in January as well. Floor is open for your questions.
Thank you, Chris. The first question is from a live viewer, Junaid Atta, who's on with us live, or Atta, who's on with us live, who asks, is Hawking radiation a real idea for the way that black holes work?
Hawking radiation is a theoretical idea. It's a hypothesis, really, and it's not been tested. It's still considered to be a legitimate concept of how black holes actually lose mass, evaporate, and therefore eventually disappear. The basis of it is the idea that in the vacuum of space, in the vacuum as demonstrated in the physics lab, virtual particle-antiparticle pairs appear and disappear, come in and out of existence for tiny periods of time all the time. It's just a phenomenon of the vacuum. The vacuum has the potential to create matter and antimatter. If this process happens near the event horizon of a black hole, there's a finite probability that one member of the pair will escape while the other member goes in. And since this is essentially borrowing something from the pure vacuum of space, the net effect is that the black hole is losing mass. Or equivalently, since E equals mc squared, it's radiating. And when you do the math, the Hawking radiation of a solar or dead star mass black hole, 5 times, say, the mass of the sun, is a few billionths of a Kelvin, so incredibly small thermal temperature that's undetectable by any method known to astronomy. And also the evaporation rate is really slow, and we don't measure mass well enough that the mass evaporation rate is measurable by any technique known to astronomy. So as was clear to Stephen Hawking in his lifetime, it's very unlikely that astronomers can test this idea directly. However, there may be indirect tests. But at the moment, it remains an unproven hypothesis.
Thank you, Chris. The next question is from Shian Smith-Pencorvo, who's on with us live, who has a question I've heard kind of commonly asked about another material, nuclear material. But Shian asks, I'd like to ask if it would be at all feasible to collect all the plastic in the world and eject it into the sun as a solution to the plastic crisis. So is that possible with any of our trash on Earth?
It is, of course, technically possible to collect garbage or plastic or trash and put it into orbit, make it leave the Earth's orbit, and send it towards the sun. Unfortunately, the energy cost of doing so would far exceed the sort of environmental savings of that, because at the moment the cost of sending material into orbit is quite high. Basically, it costs something like $10,000 or $5,000 a kilogram to send something just into Earth orbit, and that's of course not escaping the Earth. You need another 40% velocity to send it away from the Earth towards the sun and eventually into the sun. And so at that recycling cost, if you want to look at it that way, it's just completely infeasible. Basically, we just produce millions, literally millions. I think it's hundreds of millions of tons of trash a year, much of it plastic. And getting things into space and leaving the Earth is far too expensive. It would be cheaper to, of course, inter this material deep in the Earth, and it might, if it was in stable geological environments, it might not have a bad consequence for plastic to sit there. The trouble now, of course, is that much of the plastic is in the world's oceans, since the world is 3/4 covered by water. And there, it definitely does enormous damage to the environment and to the food web. So unfortunately, space is not going to save us from this problem.
All right, thank you very much, Chris. The next question is from a live viewer, Omri Baron, who asks, is it possible that we are inside a black hole?
Not likely that we're inside a black hole. What that really might mean is that we're inside an event horizon of some other larger region of space-time. Now, formally, that would be possible. If we lived in a closed universe, then in some level, for a universe that's geometrically closed by the mass energy of that universe, then you could consider the horizon of that universe to be analogous to an event horizon. So that's the only way in which we might live inside an event horizon. But in fact, our universe is, as far as we can tell, flat, which is not to say closed, and so our universe does not have that character. And in any case, the horizons that we encounter in the concepts in cosmology are not the same as event horizons of black holes, which result from the extreme compression of normal matter. So really, in practical terms, no, I don't think we live inside an event horizon.
The next question is from Bill Riddle, who sent an email asking, in the standard model of physics, there are 8 particles not involved in the structure of an atom. Things like this charm, strange top and bottom quark, and then the muon and tau electrons and neutrinos. But what role do these play in the workings of our universe if they're not part of atoms?
That's a good question. So why, and it's a question fundamental physics has a question, why so many particles? To paraphrase, I think it was Wolfgang Pauli who was talking about the neutrino when it was first discovered. Who ordered that? It was not obvious why we needed extra particles, what role they played. So the premise of the question is correct. Normal matter is composed of up and down quarks in combination. Those form protons and neutrons, which is most of the mass of the universe outside of dark matter. Dark matter we don't think is made of any kind of quark at all, but a new kind of subatomic particle. So the role of these other quarks, especially the other quarks, the strange and the charm and the truth and beauty quarks, the other 4, is not to be a part of normal matter. They are produced rarely because they have much higher mass than normal quarks and protons and neutrons, and they don't tend to form stable configurations. So we see them produced momentarily in large-scale accelerators. They're essentially exotic forms of matter or particles that only appear when we have sufficient energy to create them. Also, free quarks are not seen in nature. So even in normal quarks, the up and down quarks of protons and neutrons, those are never seen in isolation. They're essentially always seen in combination in the form of protons and neutrons. So it's an open question what the role of these other particles is in the universe or why they exist at all. And it's a question that physicists would really like to know the answer to.
Thank you, Chris. The next question is from William Spizzeri, who's on with us live, who says, the moon is moving away from the Earth and its orbit radius is increasing. Is its orbital speed increasing or decreasing?
For conservation of angular momentum, its orbital speed is actually decreasing. So what is causing the moon to move away from the Earth is a tidal interaction between the moon and the Earth. Essentially, the moon is stealing very small amounts of angular momentum, which is essentially a form of rotational energy, from the Earth, and translating that into increased distance, into increased orbital energy of its orbit around the Earth. And so 2 things are happening at once. The moon is moving away from the Earth very, very, very slowly. I think it's a few centimeters a year, maybe 4 centimeters a year. Tiny amount, obviously, compared to the distance to the moon, which is 400,000 kilometers. And in the same time, the Earth's spin rate is slowing down, and so the Earth day gets, I think, something like a millionth of a second longer every year. So both these things happen together. The fact that they happen together expresses the conservation of energy and angular momentum, and it is a normal consequence of tidal interaction between 2 objects. We might expect to see similar effects in other planet-moon systems elsewhere in the universe.
All right, so I think we'll finally get to this. There's been all this information, all this news about the star Betelgeuse, and now there's somebody has detected a gravitational wave coming from that area. What is going on? Do we know anything? What does the astronomy community know about Betelgeuse?
So I'd have to look at this potential of a gravity wave detection from Betelgeuse. I don't think that's confirmed at all, because gravitational waves really can't be isolated on the sky accurately enough to pinpoint them to an individual star. What is known, of course, is that Betelgeuse is changing its brightness recently, and it's diminishing in its brightness. by a significant amount, and that indicates some change in the energy production of Betelgeuse. We know in general terms that as a massive star, Betelgeuse has a fairly short main sequence life, something like 10 million years, compared to the Sun's 10 billion year lifetime. And we know based on measurements of its spectrum and energy state and temperature that Betelgeuse is towards the end of its life. And so it is indeed possible that it's going into some of the instabilities that result when a star exhausts its nuclear fuel and has to reconfigure to find new energy sources. As part of that reconfiguration, the star does often dim before eventually crescendoing through the nuclear fuels and gravitationally collapsing. So it's possible that Betelgeuse is approaching this state. However, these unstable phases at the end of a massive star's life can definitely last thousands of years, and it can be tens of thousands or hundreds of thousands of years. So the imminence of Betelgeuse's death, it could be, of course, very imminent. We could just be catching the final death throes, but more likely it's going to happen in the next few millennia, and it's really hard with the level of our data and our models of how stars work to be more accurate than that. But it's certainly worth watching Betelgeuse, and of course the information we're gaining about a star near the end of its life from Betelgeuse, a very bright star, is extraordinary, it's unprecedented.
Thank you very much, Chris. The next question is from one of our live viewers. Do you believe that there is a possibility that we may find some new planet in our solar system? This is from Eleazar.
We certainly have the ability and the likelihood of finding some additional dwarf planets. Remember, Pluto formally got demoted a couple of decades ago based on its properties. It's highly inclined and eccentric orbit. It's very low mass compared to the other planets in the outer solar system. All indicate that it's likely to have been captured from the Kuiper Belt, this region of space from about 40 to 80 astronomical units, where there are other rocky bodies. Since that demotion, we found several other dwarf planets. And so if we include the category of dwarf planets, and these can be large enough where gravity forms a spherical object, so they're definitely not like asteroids, which tend to be irregular objects and are substantially smaller, sort of 1,000 kilometers or smaller. So at the level of a couple of thousand kilometers in diameter, it's entirely probable that there are additional objects out there in the Kuiper Belt. And there are about 3 major surveys underway to find such objects. They're all midstream, and probably within 3 or 4 years we may have a handful more dwarf planets in the solar system.
The next question is from D. Zach, who's on with us live, who asks, what are quasars and how are they different from black holes?
A quasar is a contraction of quasi-stellar radio source. These objects were first identified as radio sources back in the early 1960s, and by 1963 some of these radio sources had been identified with bright stellar sources in the optical sky. Martin Schmidt made this discovery at Caltech in 1963. By taking a spectrum of one of these stellar objects, he showed that it had a substantial redshift, was moving away from the Earth at 1,000,000 miles per hour and was at a distance of hundreds of millions of light years. So the question then became, what could cause something to look so point-like and compact and have enormous luminosity? Because the brightest quasars are not that faint. They're not visible to the naked eye, but they're about 13th or 14th magnitude, which is pretty bright for such a distant object. And so it quickly became clear that the only plausible mechanism to make a stellar object so bright was for it to be a non-thermal energy source at the center of a galaxy powered by a massive black hole. That model became common by the late 1960s. People like Martin Rees and Donald Lynden-Bell were the theorists who were the architects of the supermassive black hole model of quasars. And so through the 70s and 80s, we found more of these objects. Now, with the Sloan Digital Sky Survey, we literally have millions of quasars identified and in catalogs, and they each have a supermassive black hole in their centers. The mass of those black holes range from 100 million solar masses all the way up to 20 or even 30 billion times the mass of the sun. extraordinary objects, but they're still quite rare. Even though there are millions of them, of course, that's to be compared to hundreds of billions of galaxies. So galaxies where the black hole is active, which is what happens when we see it as a quasar, are quite rare. Basically, all galaxies have black holes, but only about 1% of them are active at any given time. And only the most massive of those black holes, when they're active, get to be called quasars. But it's an exciting field of research, and it now attracts hundreds of astronomers to use the world's biggest telescopes to try and understand quasars better.
The next question is from Eric Cochran, who's on with us live, who asks, what contributions to astronomy and astrophysics can or do computer scientists and software engineers make? Are there any open source projects or calls for volunteers?
Computer science and programming is an enormously important part of modern astrophysics. Computers, of course, are needed to reduce the data produced by large CCDs, enormous data volumes and data rates that now for big surveys exceed terabytes a night. So computer scientists are absolutely essential in designing pipelines and methods for handling these enormous data streams, not just from surveys, but just any large telescope will have a CCD big enough to generate tens or maybe hundreds of gigabytes of data a night. So computer scientists are useful there. They're also useful in designing algorithms and methods for detecting faint signals in the presence of noise. And this is a problem that can be at optical wavelengths or radio or gamma ray or gravitational waves. Almost essentially any astronomical or astrophysical signal is detected in the presence of noise. And computer science methods are used to detect such signals. Now, some of these projects are crowdsourced and actually involve citizen scientists, and that's where amateur computer scientists, if you like, or amateur astronomers can get involved if they know these techniques. The other area where computer science plays a really important role in astronomy is in terms of simulations. So computers are now powerful to simulate quite sophisticated regions of the universe, so big regions of the universe with full complexity of gas, gravity, shock waves, dark matter, normal matter, etc. And so computer scientists are central in doing this kind of work and designing how you simulate a region of the universe in a computer. It could be a region of the universe as small as a black hole in the environment of a solar mass black hole, or it could be a large chunk of the universe where we're watching gravity cause the structures of clusters and superclusters to form. All of these methods involve the tools of computer science to do properly. And essentially any well-trained graduate student in astronomy heading towards a master's or a PhD is probably going to have to learn some significant computer science methods, and may indeed take computer science courses at the graduate level for this reason.
The next question is, and so I'm going to mention Digital Cosmos would like to know if at some point you could tell some cool stories about different of the items from your office. So I want to put a plug in. We have a few episodes of a podcast called The Star Field, and you can look for that. There's only a few episodes out, but as part of each of those episodes, Professor Impey has talked about items from his office. So we'll get to that at some point. But I appreciate that people are interested in that. Sarah Gonzalez, though, would like to know if you think that there is intelligent life in the universe or just microbial life.
It's a good question. Astronomers are all wondering the answer to this question because we have so many exoplanets now, 4,500 confirmed, and by inference, tens of billions in the Milky Way overall. With that amount of real estate, that's likely a lot of it to be habitable in terms of being at the right temperature and having liquid water and carbon-based material. It seems implausible that there's not life throughout the galaxy. And that would, of course, mostly be microbial life. Most of the history of the Earth is a microbial history, starting about 4 billion years ago. Life did not become multicellular for a couple of billion years, and it didn't become large enough to see with the naked eye on the Earth until about 500 million years ago. So logically, if life proceeds from simple and small to larger and more complex, then there's more microbial life than intelligent life in the universe. The real question is how much more? It is possible that the development or evolution of intelligent life is an unlikely thing, that it takes a long time, as it did on the Earth, that it involves some maybe unlikely events or bottlenecks in evolutionary history, and indeed only a handful of species on the Earth, being generous and including dolphins and orcas and elephants along with humans, are intelligent out of hundreds of millions of species on the planet. So in all likelihood, intelligent life in the universe is much rarer than microbial life, and it could be very much rarer. It could be vanishingly rare. It is possible that it doesn't happen very often at all, despite the raw material for it. Or it takes a long time, and so the universe is simply not old enough for much of it to have developed. We don't know the answers to any of these questions, which is why the search for life in the universe is such a compelling topic in astronomy.
Following up from our earlier question about Betelgeuse, can you talk about what it would look like in the night sky? How bright would it be if it were to go supernova? And is there any danger for people on Earth?
No, so there's no danger, to get to that part first. Betelgeuse is part of the Orion constellation and near the Orion Nebula, and that's, I think, a distance about 1,500 light years. So if it were to go supernova, given its mass and the likely, a single star supernova have quite variable luminosity. So unlike the binary star supernovae, which have a very uniform luminosity when they explode and hence are used as distance indicators in the far-off universe, single star supernovae have quite variable luminosity. But generally speaking, if Betelgeuse goes supernova, it'll be visible in the daytime sky. It'll immediately go from being one of the brightest stars already in the nighttime sky, visible to the naked eye, to being a star visible in the daytime sky. It wouldn't rival the sun, but it will be present in the daytime sky. Pretty extraordinary occurrence that hasn't happened on the Earth for about 400 years. That's how long it's been since we had a supernova in our own galaxy. But that's about all. In terms of damage to the Earth and radiation damage and so on, a supernova would have to go off within tens of light years, maybe 30, 40 light years or less, for the energy to be so large that the radiation damage would alter the biosphere or impact the ozone layer in our atmosphere. So Betelgeuse is not that category of supernova. It would just be a fantastically interesting event if it happened.
Thank you very much, Chris. The next question is from Jane Snow, who's on with us live, who would like to know more about fast radio bursts. What are they? How are they discovered? And why are astronomers so interested in them?
Fast radio bursts have been, for a few years, they were a mystery. They're sort of rapid phenomena, transient phenomena in the night sky. And again, as with gamma ray bursts and other phenomena at non-optical wavelengths, it took a while for astronomers to associate them with astronomical objects. It's likely that they're associated with compact objects, with accretion onto compact objects. They could be episodic, or it could actually be one-off accretion. So at the moment, we don't actually know very much about the mechanism behind the fast radio bursts, or even what the emission mechanism is of these radio bursts. But it is likely to be high energy radiation. These are, even radio waves have low energy in the electromagnetic spectrum, but the energy implied to create radio waves in a stellar environment, stars don't normally emit radio waves, for example, is due to compact energy sources in a collapsed stellar object. As for beyond that, the floor is still open, and astronomers are working hard to find out what's going on with the radio bursts.
Thank you. The next question is from Trey, who is on with us live, who would like to know, what are your thoughts on solar flares regarding how much of a threat they are to us here on Earth, and why would they be a threat? Maybe you could talk about for the rest of the viewers.
Solar flares, stars like the sun, normal main sequence midlife stars, suffer flares, episodic eruptions from their surface. And a normal solar flare is not a dangerous phenomenon. There are flares from the sun every few decades that put enough high energy particles into the solar wind that they could, when they eventually reach the Earth, they could cause serious disruption to radio communications. So solar flares are just a part of a star's life. They're just episodic eruptions from under the sun's surface, which is its photosphere, where magnetic reconnection or magnetic acceleration generates high-energy particles or cosmic rays and high-energy radiation. And that's what causes the effects on the Earth 150 million kilometers away. These normal flares, like I said, can cause occasional and maybe regional disruption to telecommunications. But there's a category of super flares, which are just the very extreme version of flares, which may occur only once every few centuries or a millennia. And none of those, of course, have happened with the sun in recorded history. However, if one were to occur with the sun, given our modern technological world, they would be devastating. They would essentially take down all the electrical power grids worldwide. They would cause, enormous damage because the high energy emission running through circuitry and overwhelming circuit breakers and capacitors to protect delicate electronics would cause fantastic amount of damage. So they would be almost civilization disrupting, if not destroying events. So super flares are important, and we don't understand how often they happen exactly for a sun like this star, and we don't actually have warning of them. So it makes people a little nervous about what the sun might do in the future.
Thank you, Chris. Our next question is from Gitanjali, who sent an email question, and the question is, what exactly signals the end of planet formation in a star system? For example, is planet formation still taking place in the asteroid belt or Kuiper belt of our solar system?
Planet formation, as well as we understand it, is a fairly rapid process. So when a solar nebula or stellar nebula collapses, the star ignites at the center, and the star, of course, incorporates by far most of the material in the nebula, 99 or 99.5% of the material. What's left over forms a circumstellar disk of dust and gas, and those small dust particles gradually come together by initially electrostatic forces and then gravity to build into rocky objects, planetesimals. Planetesimals are 50, 100, 1,000 kilometers across, and eventually planets are built. The entire process of collapsing to a protostellar disk and forming fully fledged planets takes about 50 million years, we think, based on simulations, and it did in the solar system, which is a tiny fraction of the age of the solar system. So that's very quick, actually, in an astronomical timescale. And then the question of does it continue after that is generally not. The process of sweeping up material by gravity into rocky objects is fairly efficient. Also, in the early stage of a sun like the star's life, it goes through a T-Tauri phase, which means it's very luminous, maybe 100 times more luminous than now. And that extra luminosity, the radiation pressure from that drives out the residual gas and dust particles. So essentially sweeps the system clean once the planets are formed. So there's very little left over. So the space between planets in a solar system like ours, a mature one, is really extremely empty. And then situations like the asteroid belt just represent a place where these processes were inefficient and a planet didn't form. If you sweep up all the material in the asteroid belt, I think it amounts to about 5% of the Earth's mass. So these are not going to form planets at any time in the future, even if you play it forward. So basically, planet formation happens quickly. It happens in a short period of time at the beginning, and it then is pretty much quenched forever.
Thank you, Chris. The next question is also from email. Howard Lester would like to know, with all the talk of Titan possibly harboring some kind of life, might it be possible to develop, he says, I'm assuming he means like multicellular life, if the sun were to become a red giant and get closer to Titan and warm it up? How would that change things on Titan and frankly in the rest of the solar system?
Hi, Howard. I've known Howard for a long time. He was a colleague of mine from the MMT a long time ago. It's Titan life is possible, even in its current frigid location. It would be a very strange form of life, of course, because the oceans on Titan are ethane, methane, with a little bit of water and ammonia, we think. And it's not clear if you can form biology in that circumstance. If Titan were closer or warmer somehow, then it's not clear that would make Titan more likely to be a biological world, because the ingredients of Titan are still so unusual, in the sense that it actually doesn't have a lot of liquid water like the Earth does, or like Europa does. So Titan's probably, the possibility of Titan being living doesn't really depend on its temperature that much, because even at its very cold location, a non-standard form of biology is certainly possible. And if it was much warmer, the ethane and methane would essentially evaporate or boil off, and the water that would be left would be not much water at all, not helping the situation. Something like Europa, of course, could be a water world with life, and if it were warmer, the ice would melt and you just have liquid oceans girdling the entire moon. So these hypothetical worlds, or hypothetical living worlds, are really interesting because they represent sort of counterpoints to the Earth itself and possible demonstrations of alternative pathways to biology. And it's interesting, given that we don't know if there's life in the universe, to consider what the alternate pathways might be. There's no reason to assume that the pathway that led to life on Earth, the particular chemical balance of the Earth and temperature and chemical composition of the Earth, is unique as a pathway to biology. So investigating these alternate pathways directly, by exploration, of course, in the solar system, is a really important thing to do.
Thank you, Chris. The next question is from Elaine Nora, who's on with us live, who asks, why can't we send robots to Mars in a capsule like Apollo and have them do all the work on Mars instead of humans? Wouldn't that reduce the risk and danger to humans traveling to Mars?
And the answer is we're doing both. So you're right, robots or rovers on Mars are always part of our plan, and they have been. So the first Mars rover, I think, was from 1995. So we've been sending rovers to Mars for decades. Spirit and Opportunity were very successful examples, and one of those two is still functioning. And now we have the Curiosity rover, and very soon we'll have its twin, the 2020 rover, sent towards Mars. And the rovers have gone in size from the size of a Tonka toy to the size of an SUV. So the rovers are getting pretty large and sophisticated. And so they are cheaper to send. It's always cheaper to send a robot to a planet than to send people who need life support and larger volume and compressed air and protection from the space environment. So NASA and other space agencies are going to continue to send rovers. And in fact, in the next instance, a series of rover missions are going to be used to get samples back of Mars to the Earth. So rather than send astronauts to bring back samples, we're staging samples from the Mars rovers, starting with the 2020, the Curiosity twin rover that's going in a couple of years. We're going to collect geological samples from interesting sites, stash them at another location, and then we'll send a subsequent mission to pick them up and bring them back to the Earth. So this method of using rover technology to bring back samples is an example of how the technology has really improved. But for some scientists, it's never going to be a complete substitute for sending people. Because if you send a trained geologist to Mars on the ground, doing their own investigation with tools and of course techniques to help them analyze rocks where they sit, that's an entirely different thing. It's just like the difference between what we learn on the Earth with remote sensing and what we learn from geologists actually going to locations. So even though it costs more, we will be sending humans to Mars. And in fact, in that case, it's not just to see what Mars is made of or whether there's life there, but as a view to potentially forming a habitat there.
All right, the next question is from David Weidman, who's on with us live, who asks, do you have any thoughts on the sun's temperature and why the corona is so much hotter than the surface?
The sun's surface temperature, as we call the surface, of course, is not a solid surface. It's the photosphere, which is the region where the plasma of the sun gets low enough density that radiation can travel freely and come in straight lines essentially to the Earth. So we see it as an edge. That temperature is 5,700 Kelvin. The corona, the region well above the sun's surface, gets up to temperatures of 1 or 2 million Kelvin, but it's a very thin medium. It's not, of course, the density of the sun is much less beyond its surface. So the density of the corona is very low, but the temperature is very high. And that has been a historical mystery for decades. We think we understand more about it, maybe don't have a full explanation, but it's to do with magnetic energy. So the sun is threaded by magnetic fields. Magnetic fields are generated and then destroyed by the sun's rotation in a dynamo mechanism that was understood by Eugene Parker, astrophysicist at the University of Chicago, in the last century, for whom the Parker probe is named. The Parker probe is probably the mission currently that's going to try and answer the question that I was just asked, which is, why is the corona so hot? The answer is we don't completely know, but the mission to answer that question is up there right now. The answer is something to do with magnetic energy. It's to do with the fact that magnetic fields, even if they're in a diffuse medium, can accelerate particles to very high energies. And the equivalent temperature of those energies is hundreds of thousands or millions of Kelvin. So in principle, there's a mechanism to get a very hot corona. But the details of how that works depend, of course, on the nature of the magnetic field, how it's generated, what's the degree of order or disorder in the magnetic field, and those are things we don't yet know.
All right, thank you, Chris. The next question is from Junaid Atta, who's on with us live, who asks, is the amount of dark matter, does it vary from galaxy to galaxy?
That's a good question. Dark matter is a ubiquitous ingredient in the universe, seen on all scales, from sub-galaxy scales up to the largest superclusters and the big voids of intergalactic space. So it's an omnipresent component of the universe that is about 6 times larger in its total weight or mass than normal matter, than the matter we're made of. It's not distributed uniformly or randomly, of course. It's subject not to the electromagnetic force, but to the force of gravity, and so it clusters and has clustered over cosmic time. It clusters less strongly than normal matter, which is subject to other forces that cause it to collapse and concentrate more. So normal dark matter is more smoothly distributed or undulating through the large-scale regions of the universe, but it does have structure. And we do understand that structure in terms of gravity, the single force operating over 13 billion years. And also we can measure the density of dark matter by the way it bends light that passes through it, so gravitational lensing. So our ability to map dark matter depends on prediction of general relativity, which is the slight deflection of light caused by mass.
Debaparna is on with us live and would like to know, if we could jump to the speed of light or near the speed of light, what would the cosmic microwave background look like? Would it be more in the visible range, or towards even more energetic like gamma rays? What would happen to that?
Yes, if you were moving at relativistic speed, then of course you would see a relativistic compression, a relativistic effect on radiation, the radiation you were passing through. So the microwaves from the background of the universe, the Big Bang, travel through space. They fill space, permeate space, traveling at the speed of light. And in fact, due to the Earth's motion, so the Earth is moving and the sun is moving around the galaxy, and the galaxy is moving in the local region of supercluster of galaxies, all of that leads to a very slight temperature difference between the microwave background in one direction and the other direction. That's called a dipole effect. And that dipole effect is at the level of a few tens of millikelvin, or tens of hundreds of a degree, basically, on the microwave background. If we were moving, and that's because our speed is hundreds of kilometers per second. If our speed were tens of thousands or hundreds of thousands of kilometers per second, relativistic speeds, then that temperature difference forward to backward would be much larger. So the microwave background would look much hotter in the direction of motion and much cooler in the direction away from motion by factors by maybe order of magnitude or more rather than by a small fractional amount. So it's just an extreme version of an effect that I actually already see due to the Earth and the galaxy's motion through the universe.
Thank you, Chris. The next question is from Elaine Nora, who's on with us live, who says, supposedly neutrinos didn't have a mass, but scientists seem to have recently found a mass for the neutrino. How did that happen? How did they find a mass?
Scientists have found the mass of the neutrino by the fact that it oscillates. So there are three, in the standard model of particle physics, there are three flavors of neutrinos. There's the normal neutrino that twins with the electron, and so it's called the electron neutrino. But there are also a muon and the tau neutrino, which pair with these other leptons, the mu particle and the tau particle. And nobody has measured the mass of any individual neutrino. But what has been seen and been inferred in neutrino detection experiments in the last decade or so is the neutrinos oscillate. As they travel through space at nearly the speed of light, they can change from one of these neutrino states to another. And so it is the oscillation of these neutrinos between the three different flavors that's been observed. And the detection of that oscillation allows you to detect a combination of the masses. It's like the difference in the squares of the masses of the two flavors of neutrinos. So that's what physicists have detected. They've detected in combination the masses of any two of the three flavors of neutrinos, but not the mass of any one. In other words, we have an indication, an indirect indication that neutrinos must have mass by measuring a combinatory version of the mass, but we've never detected the absolute mass of any one of the three flavors. It's a slightly complex or subtle explanation because the experiment is subtle. And really, at the moment, we're not sure how we would detect an individual neutrino flavor mass. The fact that they do have mass by inference, all three of the flavors, is important because it means they're a significant mass component of the universe. But the constraints on those masses are such that they cannot be a dominant component of the universe. For example, neutrinos cannot form the bulk of the dark matter that pervades the universe. We've known that for a while anyway, because neutrinos, because they travel at the speed of light, are considered a form of what's called hot dark matter. And that type of dark matter does not give the universe its large-scale properties that we observed.
Thank you very much. The next question is from Kirill Lyashko, who's on with us live, who asks, do you know something about an idea of an attractor towards which our Milky Way is moving to?
There is an idea that was first evolved in the 1980s when people started to do large-scale surveys of galaxies. So as people started to do redshift surveys of galaxies and saw voids and large-scale structures and so on, they were able to map out the motion of the Milky Way and our local group of galaxies towards these much larger aggregations, like the Virgo cluster and the Coma cluster and the local supercluster. In doing that work, they did seem to identify a region of space where the Milky Way and many galaxies around it seem to have a net motion of a few hundred kilometers per second. And the distance of this mass concentration and the speed that it was inducing on the Milky Way suggested that it was enormously massive, perhaps 10 to the power 17 solar masses. So remember what that is. A galaxy itself is about 1 billion solar masses, a trillion solar masses, including the dark matter. So we're talking about 10 to the 4 or 10 to the 5 galaxies, so a huge concentration of galaxies. And therefore, it was called the Great Attractor, because it was some vast concentration of galaxies causing us to move even at a distance of hundreds of millions of light years. The evidence for the Great Attractor seemed strong, or fairly strong, in the 1980s. A number of papers were written about it. The evidence has got weaker over time because we have much better redshift surveys, and it turns out that there's no single agglomeration of matter that has the properties you would call a Great Attractor. Rather, the clustering is more discrete. There are clusters and superclusters, but they're more concentrated and more isolated from each other. And so there's no single object with the mass that was imputed to the Great Attractor several decades ago.
The next question is from William Jennings, who sent an email asking, will the speed of spacecraft increase significantly in our lifetimes to enable humans to travel to Mars in weeks or days rather than months?
Unfortunately not. The constraints on space travel are still pretty strong because it's an energy cost. I think the fastest spacecraft that we humans have ever produced travel at a speed of about 100,000 miles an hour, and those are spacecraft that head to the inner solar system. So they're getting some of their speed boost from a gravity assist from the sun, large object at the center of the solar system. For objects that leave Earth orbit and then go to another planet, really the matter of saving energy is really important, because all the energy you have to put into rocket fuel to get to a distant object, you also have to lift off the Earth against the Earth's gravity, and that's very expensive and hard to do. So objects have optimal trajectories in space, given the orbits of the planets, you say the Earth and the Mars, if you're going from the Earth to the Mars. And those optimal orbits, that trajectories rather, that save energy tend to not be very fast, and that's why you end up with an 8 or 9 month journey to Mars for saving energy. You could do it faster. You could do it maybe in 1 month if you pick the time in the orbits when the Earth and Mars are closest to each other, a distance of only 50 million miles. You could do it much faster, but the energy cost will be enormous, and people essentially don't want to pay that cost because it makes the mission very expensive. So that improvement is not going to happen just because the energy cost is too high. To do much better still, you'd of course need a different form of propulsion. And since we're still using chemical rocket fuel, albeit efficient and highly volatile rocket fuel, it's chemical energy. And so until we have an alternate form of propulsion, we're never going to get to the planets much faster than we do now.
The next question is from Omri Baron, who's on with us live, who asks, can life be based only on the element carbon?
Life is based on carbon, the life we know. The question of whether it needs other, and there's two ways to interpret that question. One is whether it needs more than just carbon, and the answer is yes, it does. Life, biology as we know it, is carbon-based, but it involves a minimum set of nitrogen, oxygen, potassium, and a few other elements. So there's this little set of about 7 or 8 elements beyond carbon that are required to make biochemistry work. And if you get down to trace elements that are important, you know, even in human physiology, then you're talking more like 15 or 16 elements. So you can't really make complex biology of the kind we have on the Earth without a suite of elements of order a dozen, say. But carbon is definitely the basis. Could that suite of elements not involve carbon and involve something else and not have carbon at all? That's pretty difficult to arrange. Silicon is in the same column in the periodic table, and so has similar electronic properties and combinatory properties, but is not as good at forming long, stable molecules as carbon. It's just a matter of chemistry, nuclear chemistry as well. So life could be based on not carbon, possibly, but no one's shown, even in a lab or even theoretically in a computer, how that would work. And even if you could make complex molecules and reaction networks of molecules, there's no sense that you could get replicating molecules, a stable cell, and the complexity of life as we see on the Earth.
Thank you. Carol Bodderton sent an email. Apparently there was a NOVA program about Jupiter, and it said that Jupiter possibly once moved closer to the sun and then out to its present orbit. Can you talk more about that, and what's the evidence for something like that having happened?
So planet migration is now a core principle in how solar systems evolve. And it is now fairly clear that the planets in the solar system have not always been in their current positions. In fact, there have been a series of moves. It's not as simple as Jupiter moving in and then back out again. The biggest movements, in fact, were Uranus and Neptune, which started much closer in than where they are now and eventually shifted outward. Most of these migrations happen in the first 500 million years of the solar system. So well after the planets formed, when resonances between the planets in their orbits, or gravitational couplings between the planets, cause them to be unstable in their orbits and therefore move either in or out. So these movements depend very much on the initial conditions of a solar system. If you form the solar system, our solar system, with different initial conditions, a different set of planets or a different set of starting positions, then the ending positions after 4.5 billion years of evolution would be different still and different from the ones we see. These effects are nonlinear. They're subject to small perturbations. In other words, a small initial impulse can lead to a large eventual outcome. And so they're very hard to predict. They're almost not deterministic. So it's a very interesting field of astrophysics because it's very hard to take a starting configuration of a solar system and predict exactly what it will look like billions of years later.
Excellent. Thank you very much. The next question is from Matthew Mucker, who's on with us live, who asks, why does our solar system have a circumstellar disk? Why is it not a sphere?
Well, it's possible you could just have a purely spherical gas configuration that would collapse spherically and lead to a star and maybe nothing else around it. But random motions in chaotic regions of space tend to lead to a little bit of net rotation. So if you look at turbulence theory, this is theory that goes back to Kolmogorov and physicists 100 years ago. Then you look in a region of gas where eventually gravity will collapse a situation, it's likely to have a small amount of net rotation. And so if it has a small amount of net rotation and it collapses by gravity, then of course it will have angular momentum, and the conservation of that angular momentum leads to the likely formation of a disk. So the formation of disks in astrophysics is a pretty common phenomenon given that there is turbulence in the chaotic gas situation, and so there's a small amount of initial rotation in a large diffuse gas cloud. As it collapses, conservation of angular momentum says that rotation speed will increase as the object gets smaller, conserving angular momentum, and that's the basis for the formation of the planets around stars that we see as a pretty common occurrence in the universe.
Thank you. The next question is from Tech Ideas, who is on with us live, who asks, we always seem to measure something relative to something else. Is there any object or particle that is not relative to anything we know? Why do we talk about relative motion and relativity all the time?
It's a good question. We do mostly because we're in a universe, a multi-scale universe, where the phenomena we see around us are operating on many different scales. So you have to select the scale of interest. And if you go to a different scale, you'll see something different. Motion is the perfect example because this Earth is obviously spinning and going around the sun, which is going around the Milky Way every 250 million years. The Milky Way is part of the local group, which is moving towards the Virgo cluster, and the Virgo cluster is part of a local supercluster and has motion with respect to that. And so if you go up eventually in big enough scales, you reach the level of what's called an inertial frame. That is to say, a large enough fraction of the universe that is not moving because you're representing the entire universe. And that's the point at which you see the microwave background radiation at equal intensity in every direction. So that's the place where we don't have to talk about relative motion, where we talk about absolute. The temperature of the microwave background is an absolute number. It's 2.724 or 2.726 Kelvin, very precisely measured. And the direction of our motion with respect to that background, the sum of all the motions of galaxies on smaller scales, is also a well-measured number. So probably in terms of motions, we do have some absolutes there because we know, in a nonsensical sense, the universe is obviously not going anywhere, so we measure ourselves with respect to the universe, and that is an absolute motion. For other motions, and temperature can be measured on an absolute scale as well, the Kelvin scale for all sorts of astrophysical phenomena. So not everything is measured relatively. But in general, in science and certainly in astronomy, relative observations, differential observations, are often easier than absolute observations because it's a question of calibration and errors and systematic errors. It's just easier to do a differential measurement. That's true in physics as well.
Thank you, Chris. The final question for today is from Raumfahrt Exploring Space, who asks, do we take account of multiple dimensions while detecting like greater than 3 dimensions when detecting exoplanets or objects through microlensing or any other existing methods? Does it have any practical implications?
Not really for astrophysical observation. So the possibility, and indeed the likelihood, if you believe in string theory, that the universe has an underlying substrate reality that's multidimensional beyond the 3 dimensions of space and time that we see around us. The question is, does that have any manifestation in the universe we measure with our telescopes and in the laboratory? And the simple answer is no. So we can do almost all of the astronomical measurements of the microwave background, of gravitational lensing, of the mass of things, of trajectories in space, without invoking any higher dimensions. It's come down to a lab physics question of whether physics experiments can be designed cleverly enough to tease out the presence of those hidden dimensions, but just by constructing a very controlled situation in the lab. And there are some people that are still optimistic that these lab experiments will be able to show the imprint of extra dimensions. But for routine astronomical measurements, we are pretty safe in ignoring these extra dimensions. Thanks again for your questions. Again, everything from exoplanets to extra dimensions. So very good range of subject matter as always, and we'll be back with you in a couple of weeks. Thanks to Matthew for help with the session.